Hi. In today's lesson, we're going to talk about the buoyant force. Now, the buoyant force, questions about buoyant force account for probably about a third of the fluids questions you're going to get on the AP test. So it's important to understand it. The good news is it's not that hard to understand. Okay, so let's get on it. So basically, the buoyant force is a net upward force that acts on an object that's submerged in a fluid, be it a liquid or a gas. And it results from the fact that the hydrostatic pressure at the top, which remember is rho GH, is going to be smaller than the hydrostatic pressure at the bottom. And that results in a net upward force on the object. The buoyant force is a result of collisions. So basically, the idea is let's just look at the sides, okay? If I look at the sides, there's no net sideways force because the magnitude of the net collisional force on this side is equal to what it is on this side. However, at the top, the collisions involve less force than the ones on the bottom. So the idea is the net collisional force at the bottom is greater than the net collisional force on the top, making a net upward force, whereas the net collisional forces on the sides cancel each other out. Okay, now the magnitude of this force is, and this is what you really need to know, it is always equal to the weight of the fluid that is displaced. So in other words, if I have this object here, let's say it's a 5 kilogram object and it weighs 5 newtons, surprise, 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 it is not displacing the fluid. And the fluid comes all the way up to the top. This is supposed to be, this is my artwork here, okay? This is supposed to be a container with a spout, and there's a little base I'm going to catch it in. So right now there's no displaced fluid, so the weight of the displaced fluid is 0. So there's no, the magnitude of the upward force on it, the buoyant force on it is 0. We're going to ignore air, okay? Now, I lower it into the liquid, and when I do, I end up displacing an amount of liquid equal to the volume of this object. Right? And that's important to keep in mind. It displaces its volume, but the buoyant force is equal to the weight of the displaced fluid. So I displace this much fluid because of its volume, and when I weigh it, I see it's 0.2 kilograms worth of fluid that came out, and that has a weight of 2 newtons. So the net upward force is going to be 2 newtons. Therefore, 2 newtons up and from the buoyant force and 3 newtons up from the tension force equals the 5 newtons down from the mg acting on this object. Now, this is referred to as Archimedes' principle. Archimedes was this Greek guy who figured this out about 3,000 years ago. Yeah, you should read about him. He's a pretty cool character. But anyway, this is sort of his big idea, one of his main big ideas that has been, I guess, lauded throughout the ages. Okay, so let's apply Archimedes' principle then to a kind of typical problem, although this one's going to be more mathy or calculation based. But here we go. Let's just say I have a metal bar. It has dimensions 4 by 4 by 10. It has a density of 7 grams per milliliter. Now notice I'm using grams and milliliters and centimeters. You've got to be careful because the system that we always use is the MKS system. That's meters, kilograms, seconds. And it's really important that your mass is always in kilograms and that your MK, and that your any kind of linear distances are measured in meters. Okay. Otherwise, because you got newtons, and that is based on that, you've got meters per second. So it's very important that we keep this in mind. So here you go. The first thing I'm going to do is I'm going to figure out what is the volume of the displaced fluid. And then I'm going to use the density of fluid to figure out what its weight is, okay? So, and I'm not going to change it into the MKS system until I have to. So I was given these units, I'm just going to go with those. So I have how much of this is actually submerged? Well, it's going to be 4 by 4 times 3, which gives me 48 cubic centimeters. Okay, so I'll say, well, density equals mass over volume. So the density of this fluid, not of the, remember, I don't care what the density of this bar is. That has nothing to do with the buoyant force. It's the density of the fluid. So I'm going to say 1.4 grams per cubic centimeter for the density of the fluid equals the mass of the fluid over the volume of the fluid. So when I solve for the mass, I get 67.2 grams. So that now I got to turn grams into kilograms to use the MKS system. So remember, you just divide grams by 1,000. That gives you kilograms. Let me move my face out of the way here. Now to find the buoyant force, I just have to say, well, the buoyant force is equal to mg of the displaced fluid. So I just multiply that by 10. I get 0.627 newtons. All right, that's a very typical kind of calculation-based question you might get asked. Okay, so again, the buoyant force can best be described this way. And this is one that you need to just memorize, okay? Since density equals mass over volume, mass is equal to density times volume. So what I can say then is the buoyant force is going to be equal to the density of the object times the volume of the object times the gravitational field strength, or if you prefer, the acceleration of gravity. So again, buoyant force equals the density of the displaced fluid, the volume of the displaced fluid, ng. All right, so let's just take a look at a couple questions we might get like this. And if you already get the idea, just skip through the video to a different part of it. But I'm just going to walk you through a couple of these. Okay, so let's just say I have this. I have a 600-gram object hanging from a string, and the tension on the string is 6 newtons. I have a container that has 100 milliliters of some fluid in here. Uh, and let's see, I forget what it is. Oh, we don't know what the density of fluid is at this point. Okay, so I lower this object in, and when I do, it's going to displace a volume equal to its volume. Right, so I went from 100 milliliters to 250 milliliters. So that means there was 150 milliliters of displaced fluid. And remember, the nice thing is a milliliter is equal to a cubic centimeter. So that's 150 cubic centimeters. So if I want to know what the density of the block is, it's pretty easy. I know what the mass of the block is. It's 600 grams. I know that it displaced 150 cubic centimeters worth of water. So I know that the density is 4 grams per cubic centimeter. Now, remember, it's really easy to turn grams per cubic centimeter into kilograms per cubic meter because you just multiply by 1,000. So if it's 4 grams per cubic centimeter, it's 4,000 kilograms per meter. This is a very easy conversion, one you need to get used to. But now let's try this one here, because that was pretty straightforward. Okay, just mass and volume, right? But now I want to know what the density of the fluid is. Okay, that's a more likely question for them to ask. Okay, so if I want to find the density of the fluid, I say, well, in order to do that, I need to use this equation here, that the buoyant force is equal to the density of the fluid, which is what I'm looking for, times the volume of the fluid, and g. Well, let's think about this. I know that the amount of fluid that was displaced was 150 cubic centimeters. In order to do this, though, if I want to use g, which is in meters per second square, then what I need to do is I need to convert this into cubic meters. And the way you convert it into cubic meters is you divide it by 1,000,000. So that, again, that's a conversion that's worth knowing. There are 1,000,000 cubic centimeters in 1 cubic meter. So if I divide this by 1,000,000, I get this. And if you forgot, 1,000,000 is 1 followed by 6 zeros. So now I know how much volume was displaced. Now I need to know what the buoyant force is. Well, the buoyant force is this. If this was 6 newtons before it went in and it's 4.8 newtons now, the difference between that is the buoyant force. So the buoyant force in this case is 1.2 newtons, the difference between what the tension force was before I put it in and when it was submerged. Now I can use this equation. I say 1.2 newtons of upward force is equal to the density of fluid times the volume of the fluid in cubic meters times the gravitational field strength G. And what I find is I get 800 kilograms per cubic meter, or if I want to divide that by 1,000 to put it in terms of what we often use for talking about substances in grams per cubic centimeter, it'd be 0.8. Okay, we'll just do another one. Again, if you understand this, just keep moving on. But what if I have something that's not on a string? Well, it's just floating there. Okay, so I have this 0.4 kilogram sphere that's floating in a liquid. It has a radius of 5 centimeters, so it's pretty big. Okay, and it's halfway submerged. Okay, I got to keep that in mind. So it's 1/2 of its volume is what's actually underwater, or so it displaces 1/2 of that. So here's what I know. Since this is zero point 0.4 kilograms, mg would be 4 newtons, and it's floating there, which means that if gravity down is 4 newtons, then the upward force of buoyancy must be 4 newtons. So I know what the buoyant force is. I know that the volume is half of the volume of the sphere. So then I just say, okay, I'm going to use this equation again, which you better put in your memory banks. The buoyant force is equal to density times volume times g. So, what is the volume of the displaced fluid? Well, the volume of the displaced fluid is 1/2 the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. That will be on your equation sheet, but hopefully you already have that in your head. So, and since r is 5 centimeters, or 0.05 meters, remember, you gotta be in meters. You cannot use centimeters. I come up with this. It's basically 0.00026 meters cubed. So that I can then substitute for V. I know what G is. I know what the buoyant force is. And now I find that the density of fluid is 1,538 kilograms per cubic meter. Or if I divide it by 1,000 to get grams per milliliter, I find 1.5. So a little more dense than water. Okay, now let's just talk in terms of, there's a little shortcut we can sometimes use for things that are floating. Okay, so I have a rectangular block that's floating in a liquid of density 1.2 grams per milliliter, and it's floating in such a way that it's 80% submerged. And I want to know what the density of the block is. Well, so what I say is the density of the block is basically can be found by saying, well, here's what I know. I know that the density of the block times g, that's the downward force, is equal to the buoyant force, right? And the buoyant force is equal to the density of liquid times the submerged volume times g. So I just set this up. I can cancel out my g. So I have the mass of the block is equal to the density of the liquid times the volume of the block that is submerged in the liquid. And so what I can say then is the density of the block is equal to the mass of the block over the volume of the block. That's the definition of density. But I can then substitute this with this. And at the end of all this, I get that the density of the block is equal to the density of liquid times the volume submerged uh, of the total volume divided by the total volume, which basically is the percent that's submerged. So that's a pretty cool thing. Take the percent that's submerged, multiply it by the density of fluid, and there you have the density of the block. All right, so that's a great shortcut to know. If you want to know the density of an object, you just say the density of the object is equal to the density of the fluid in which it is submerged or floating times the volume that is submerged divided by the total volume of the object. Now, often they're going to ask you to figure out the density of the fluid instead of the density of the object, in which case you just need to know this one right here, and you just rearrange it for the fluid. So if I just rearrange this equation here for the fluid, I get this one here. And let's just try this again. It's really not that hard to keep in mind. The density of an object is going to be equal to the density of the fluid times the percent of the object that is submerged in the fluid. Okay, now let's talk about the forces involved here in terms of Newton's third law. And this one sometimes is a little bit hard to get into your head. Let me move my face out of the way here. I'm sorry that this video is going a little bit long, but what are you going to do? Okay, so let's just say I have this 0.5 kilogram object that's hanging on a string, so there's 5 newtons of tension force. I lowered into, so now look at this. I've got a container of water here, and the total mass of this container and the water is 10 newtons, 1 kilogram. Okay. Now I'm going to lower this into here. And what I'm going to find is that when I put this in here, the buoyant force is going to reduce the tension force to 3 newtons. So I know that means, therefore, there must be 2 newtons of upward force. But Newton's third law tells me that you can't push up on this object without the object pushing down on the fluid. Again, the fluid cannot push up on the object without the object pushing down on the fluid. Well, if I push up with 2 newtons here, it must push down with 2 newtons here. So this reading will go up to 12. It's just basic Newton's third law. It's just weird for us to think in terms of fluids because they're just harder to wrap your head around, but the same rules apply. Now, let's see, every time I move my face, it seems to try to make this a little bit weird. Let's see if I go. There we go. Okay, so let's draw a free body diagram, shall we? So here is the metal ball before it goes in. Okay, so before it went in, free body diagram, I have mg down, which is 5 newtons, and I have tension up, which is 5 newtons. The object has a net force of 0. I lowered into the liquid, and what I find is, oh, I'm sorry, I'm just looking at the density of the liquid. No, I'm not looking at the density of the liquid. I'm looking at the forces acting on liquid. Sorry about that. I'm not going to change this video at this point. I'm too far into it. I'm committed. So I have, let's just say that I zeroed this with the container on here. So what I have is 10 newtons of liquid. So therefore, the free body diagram for liquid would be 10 newtons down for mg, 10 newtons up from the normal force that's being pushed up on this, which is what this records. But now I put it in there. Let's see what we have. Now, this is what you've got to get good at. Let me move my face out of the way here. I'll move my face up to here. How's this? Okay, look at this. So when I lowered it in, remember this went to 3 newtons. The tension force is 3 newtons. That's because I have 2 newtons of upward buoyant force. Now, the downward force of this object, gravity doesn't care where it is going to pull down with 5 newtons. So I know the mg is 5. I know that the tension force is 3, and therefore the buoyant force is 2. The sum of these forces equals 0. But now look at this. There is an action-reaction force here, and that is the buoyant force. So that if the buoyant force is pushing up with 2 newtons on this side, it must be pushing down with 2 newtons on on the fluid. So what I have is the fluid we determined had a mass of 10 uh, of 1 kilogram, for therefore 10 newtons. So I have 10 newtons down. That's the weight of the fluid, the pull of gravity on the fluid, plus 2 newtons because of uh, the buoyant force, the action reaction force. So that means the normal force, okay? The normal force being pushed up here has to be 12 newtons. But think about how interesting this is, okay? Before I put this in here, this said 10 and this said 5. When I put this in here, this went down by 2 and this went up by 2. It shouldn't be surprising. It's just fluids are hard to think about, right? But that's why we're going to practice. All right, let's try here. Okay, so let's try doing it without calculations. So I have a sphere of mass m, and it has a density of d. I place it in a liquid that has a density 4 times that, so 4d, all right? And the mass of liquid is 8 times the mass of this object here, and the container has negligible mass. So what I'm going to do is I'm going to put this in here. Since this has a quarter the density of this liquid, it's going to want to float. So what I do is I tie a string to it and hold it to the bottom. They love asking this question, okay? Get used to these questions where you have a tension force that's holding an object underwater or under some fluid, okay? Let's just try this here, all right? Okay, so let's try to do free body diagrams for both the sphere and the container that's holding all this. Okay, so let's start off with the sphere. The sphere has a mass of m, so therefore obviously it's being pulled down by gravity with force, gravitational force mg. Now what I want to find is the tension force. So here's how I'm going to do that. I'm going to say, well, here's the thing. Since this fluid has a density that's 4 times that of this object, then the volume of this object is going to displace a mass of fluid equal to 4m because it's got 4 times the density and the same amount of volume. So therefore, the upward buoyant force is equal to the weight of the displaced fluid, which is 4mg. So now I know that the sum of the forces has to add up to 0 because this object is at rest. So therefore, 4 up and 1 down means the tension force has to be equal to 3mg. Now, tension is an action reaction force, and so is the buoyant force. And so now I'm going to come over here. I'm going to try to look at what happens with the container. Okay, so now let's just look at this here. So let's start off with this. I know that since tension is pulling down on this object with 3 mg, it must be pulling up on the container with 3 mg. And since the buoyant force is pushing up on this object with 4 mg, it must be pushing down on the container with 4 mg. And I know I have 8m worth of liquid here, so that gives me 8 mg worth of gravitational force. So now I have 8 down and 4 down. That's a total of 12. Tension force is pulling up on the container with 3. This container is at rest, so therefore I can find that the normal force is being pushed up on here, which is what would be recorded by an electronic balance, is 9 mg. And hey, think about this. If you have 8m worth of fluid and you add 1m worth of object to it, you get 9m worth of matter that you're having to hold up. Okay, so that's pretty cool. So it's a little bit counter. The trick is you have to think in terms of the fact that both tension and buoyancy are action-reaction forces. Okay, let's do one more. Okay, so I've got now this is kind of weird, but I've got a 240-gram balloon. That's a pretty heavy balloon. It's a big one. And I'm going to fill it with helium. And helium has a density of 0.16 kilograms per cubic meter. And I'm going to fill it as a volume of 1 cubic meter. Keep my life simple here. The balloon is now attached to a 1 kilogram mass, which is being pulled down by gravity with 10 newtons worth of force. So I have an electronic balance that's reading out in terms of force. So I see that the normal force acting up on this right now is 10 newtons. It says 10 newtons of mass. That's not very well phrased, okay? And it's at rest on this electronic balance. But now I hook the balloon to it, and when I do, this reading goes from 10 to 2. And what I want to know is, what is the density of the air in which this balloon is floating? Pretty typical kind of question you're going to get asked. Let's see how you do these, okay? So first of all, remember, the way you're always going to solve these problems is you're going to say, well, the buoyant force is equal to the density of the fluid in which the object is submerged, so the density of air, times the volume of displaced fluid, the volume displaced by this 1 cubic meter balloon, times the acceleration or gravitational field strength of gravity. Gravitational field strength by acceleration of gravity. All right, so let's do this. First of all, let's draw an FBD for the metal mass, okay? So over here. So what I know is it's being pulled down by gravity with 10 newtons of force. So mg down is 10. And I know that the normal force is equal to 2 newtons. So therefore, I know the tension force must be equal to 8. Let's think about this again. It's being pulled down with 10. It's only reading 2. So that's a normal force pushing up on it. That's all this tells us. How hard am I pushing up? I'm pushing up 10 here. Now I'm only pushing up with 2. So that means I must have a tension force of 8 newtons. And I'm going to need that in order to solve this next part of it. Okay, now I'm going to draw a free body diagram for the balloon in order to determine the buoyant force on that. But to do this, I've got to figure out what the total mg of the balloon is, right? Because I have both a balloon, the shell, right, the rubber shell, and then I have the mass of the gas inside. So the mg of the balloon material, I'm told I have 0.4 kilograms. So that's 2.4 newtons worth of rubber material enclosing the helium. Now I got to find what is the mg of the helium inside there. So I'm just going to say, well, if density equals mass over volume, I know I have 0.16 kilograms per cubic meter of density. I have 1 cubic meter of it. That gives me 1.6 newtons worth of weight of helium in there. So the total weight of the total mg on the balloon, the rubber and the helium together is 4 newtons. So I can draw my free body diagram. I say, well, mg is 4 newtons down. Remember that tension force that was lifting up on the metal mass is pulling downwards on this. So that's 8 newtons. So now, because again, I have to use that action-reaction concept here. So now what I have is a total of 12. So I know the buoyant force must be equal to 12. So the trick here is I had to figure out what the mg of the balloon was and combine it with the tension to figure out what the buoyant force is. And this is great because it's making us review a very fundamental concept of physics, which is using free body diagrams. So now I can go ahead and say, well, the buoyant force is equal to the density of the fluid times the volume of the fluid, the displaced volume, times g. So I have 12 newtons of buoyant force. I don't know what the density of air is. I have 1 cubic meter of displaced volume of air times g, and I get 1.2 kilograms per meter, or 0.0012 grams per cubic centimeter. Sorry this is so long, but thanks for watching.